Inside these blue roofs, a giant machine is being born.
In the next minutes, you'll see design become steel, cables, and composite, step by step. You've only seen the body. When the 153-meter blades appear, and you'll understand why they call it colossal.
Every surface, every fastener, every inspection here determines whether it survives salt, wind, and time offshore.
And next, the blades, 153 meters each. That's when the scale becomes real. Power electronics generate heat. Cooling is not optional, it's survival.
Metrology turns looks right into is right. Microns here protect decades offshore. This white nacelle is the turbine's body, where mechanical power becomes electricity.
Every surface you see will face salt, typhoon gusts, and constant fatigue offshore, so precision starts here.
And these are the blades, 153 meters each. This is where the scale becomes real.
The factory phase has one mission: deliver a complete machine, verified and documented, before it ever touches a port.
Offshore, every repair is slow and expensive, so we remove uncertainty here.
At this scale, millimeters are not small. They become vibration, fatigue, and downtime.
Every critical part must have a history: who built it, who checked it, and what it passed.
These blades are not just long. They must match each other perfectly as a set.
Before release, we test the nervous system, controls, sensors, and power electronics, because the ocean won't wait for debugging.
Build, verify, document, then we hand it over to logistics. That's the factory's finish line.
Design freeze is the point where decisions stop moving. Every parameter is locked, so the factory can build without doubt.
We freeze the entire chain: how wind becomes torque, torque becomes electricity, and electricity becomes stable grid power. If we don't design for worst-case events now, the turbine will meet them later, unprepared.
The blade is aero and structure at the same time. Shape for efficiency, stiffness for survival.
Materials are frozen too. One uncontrolled change can create mismatched strength across an entire blade set.
Offshore salt mist doesn't forgive gaps. Sealing is reliability engineering, not cosmetics.
Power electronics are heat engines in disguise. Thermal margins must be locked before assembly.
Once this is confirmed, the factory moves fast, because everyone is building the same truth.
This is the start of a 153-meter blade, an aerodynamic shape built from controlled layers.
Before any fiber touches the mold, we verify geometry, because the mold defines the blade.
Fiber direction is the blade's skeleton. Wrong orientation means wrong stiffness.
Layer by layer, we build the airfoil, outside shape, and inside strength at the same time.
This spar cap is the backbone, designed to carry offshore loads for years. Core placement controls weight and stiffness. Gaps become weak spots, so we remove gaps now. Vacuum bagging turns hand layup into a controlled system. One leak can ruin the whole infusion. Infusion is timing and flow. Resin must reach every section evenly, from root to tip.
Uniform flow means uniform strength. This is where hidden defects are prevented. When infusion ends, we lock the result. Then curing makes it permanent. Curing is chemistry under control. Temperature and time decide the blade's final strength.
When it comes out, it won't just be long. It will be precisely shaped to turn wind into megawatts. After blades, the hub is the next critical interface. Its bolt circle must be perfect.
Here we don't just remove metal, we create alignment that controls loads for decades. Metrology turns looks right into is right. Microns here protect offshore reliability.
Flatness and concentricity decide whether the rotor sits true or fights itself with fatigue.
Offshore corrosion starts at edges and interfaces, so protection begins before assembly.
Modules are built on skids, so geometry can be controlled before they enter the nacelle.
Every lift is rehearsed. Balance first, then movement.
Machine it, measure it, protect it, then it's ready to become part of the nacelle.
This is integration. Mechanical muscle, electrical power, and control intelligence become one machine.
We treat every critical module like surgical equipment. Slow, verified, and controlled.
Millimeters here decide pressure, vibration for your ears.
Shims look small, but they lock the geometry of a 26 megawatt drivetrain.
Torque isn't a feeling, it's a controlled value, verified and marked. Good cable routing prevents heat, abrasion, and failures you can't see.
One loose connector can shut down a turbine, so every connection is verified by hand.
Our electronics generate heat. Cooling is not optional. It's survival.
Sensors are the turbine's senses. Clean signals keep control decisions correct. Salt mist will find any gap, so we hunt gaps before the ocean does. Control wiring is mapped and labeled, so offshore troubleshooting stays fast and certain.
When mechanical, electrical, and control systems share one shell, we're no longer building parts. We're building a turbine.
Before anything leaves this factory, we measure it, because offshore you can't fix guesswork.
Ultrasound finds what eyes can't: voids, delamination, hidden weakness.
Laser alignment turns geometry into numbers, and numbers into reliability.
If a flange isn't flat, bolts become springs, and fatigue starts early.
Torque isn't a feeling, it's a controlled value, verified and marked.
Salt and humidity punish weak insulation, so we test margins now.
A turbine must be safe before it can be powerful. Grounding is non-negotiable.
Traceability is the turbine's memory. Every critical part has a history. Sensors must be right, or the controller makes wrong decisions.
When measurement is complete, we don't ship hardware. We ship proof. FAT is where the turbine proves it can think, sense, and protect itself before it ever leaves the factory.
We power up the nervous system step by step, no shortcuts.
If sensors lie, control becomes blind, so every channel is validated.
Pitch control is how we tame wind loads. Smooth response matters. Yaw is steering. If it's wrong, the rotor fights the wind instead of harvesting it.
Converters handle enormous power. Thermal and voltage stability are mandatory.
A turbine must fail safe every time.
Real faults happen fast, so the controller must react faster.
When heat stays controlled, reliability stays possible.
This is the moment it stops being an assembly and becomes a verified machine.
Roll-off is the handover moment. After design, build, and FAT, the factory releases the machine.
Before the nacelle moves, the cradle must be perfect because the road will shake everything.
Transport vibration can undo months of work, so we protect every interface.
This is the last gate. Every checklist closed, every record filed.
For the factory team, this feels like a launch.
From here, logistics takes over, but the factorial's job is done.
Every centimeter is managed because this machine is too large for mistakes.
The factory chapter ends here. Next, come the journey.
Risk 3, salt mist. We control it with sealing inspections and corrosion protection before the ocean finds gaps.
Risk 4, missing history. We control it with traceability. Every part, every test, every signature.
Process turns risk into control, and control is what makes offshore power possible. The factory chapter is complete. Now the real-world constraints begin.
From this point, every turn, every bridge, and every gust of wind becomes part of the engineering. Logistics is a project of its own. Route planning, port handling, and weather windows.
Next, we follow this turbine out of Fuzhou, toward the port and the test base.
Part B, transportation. Let's see how you move a 26-megawatt giant. How do you move a 600-ton class nacelle through the real world without breaking anything? This isn't a shipment. It's an engineering operation, measured in millimeters and risk. And this, one blade, 153 meters long. Wind turns it, but logistics must deliver it first. Each blade weighs about 83.5 tons, and it behaves like a sail in crosswind.
In this chapter, we'll follow every step, from factory gate to port, across water, and into the test base.
We're moving owned a few key packages, but each one is extreme in either length or weight.
Package 1, the blades, 153 meters long. The challenge is not just size, it's geometry, deflection, and crosswind.
A blade behaves like a sail. Crosswind can turn transport into a stability problem.
Package 2, the nacelle, over 500 tons, often described as 600-ton class. Roads, bridges, and port capacity decide everything.
For weight, the game is distribution. Spread the load, protect the pavement, and stay inside legal limits. Not every port can handle these weights. Sometimes the solution is row-row ramps, not cranes.
There are tens of thousands of parts in a turbine, but transport pain concentrates in a handful of oversized packages.
Length fights corners and wind. Weight fights roads and ports. And we have to win all of it, every day, every move.
Before leaving the factory, we don't wrap these parts. We engineer their packaging.
Every contact point is defined. Pads, protector, and load paths that won't bruise the composite.
We lock the center of gravity and lift points because one wrong pick can damage structure you can't see.
We ship with sensors, tilt, shock, vibration, so the road can't lie.
Tie-down isn't brute force. It's a pattern, a sequence, and a verification.
Every critical clamp gets a torque mark because transport vibration tests everything.
When the pack is complete, we have hardware, data, and documentation moving together.
Only after technical packaging is done do we let the convoy move, because the first bump starts the real test.
Route planning starts on screens, but it's validated on the ground.
For a 153-meter blade, the first question is, can it physically turn?
Overhead clearance is a hard limit. One cable can stop a convoy.
For the nacelle, weight is the enemy. Every bridge becomes a yes or no decision.
We choose equipment to spread load, more axles, lower ground pressure, safer pavement.
Nothing moves without permits. Every kilometer must be approved, scheduled, and coordinated.
We often move at night. Less traffic, tighter control, and safer turning space.
When roads can't guarantee safety, we shift to sea, because water carries weight better than asphalt.
The last mile is often the hardest. Tight roads, real obstacles, and no room for error.
For extreme weight, we protect the road first. Mats, plates, and controlled axle loads.
We don't drive a nacelle. We choreograph it through every junction.
Multi-axle steering is how we make impossible corners possible.
For blades, the enemy is wind. Crosswind can turn a blade into a sail.
Every stop is a control loop. Check straps, check tilt, check weather, then move again.
Keep it coming slow, driver. Clear on the left. Confirmed, steady as she goes.
If wind crosses the limit, we wait, because schedule never outranks safety.
When the port lights appear, it feels like progress, but the most delicate lifts are still ahead.
Ports amplify risk, heavy lifts, tight windows, and surfaces that must carry extreme loads.
Before lifting anything, we prove the ground can hold it, because a sinking pad is a failure you can't recover from.
Not every port can lift a 600-ton class nacelle. Capacity decides whether we crane lift or choose ro-ro.
Ro-ro turns lifting into rolling, but it demands perfect alignment and perfect timing.
Tide is a hard schedule. Miss the window and you don't move today.
At this weight, you move in centimeters, not meters.
Every hold point is locked and verified, because gravity doesn't negotiate.
At sea, the load must survive vibration and roll, so we fasten it like it's going through a storm.
Blades are the opposite problem. Light enough to move, long enough to catch wind.
All right, easy on the swing there.
Slow her down, coming into position now.
Roger that, lowering 5 meters.
When the port signs off, the shipment becomes a voyage, and the ocean becomes the next test.
Getting on the ship is only the start. Sea transport has its own physics.
Defastening is the real safety system. Chains, weld points, and tension checks that fight roll and vibration.
We don't guess what the sea did. We record it. Tilt, shock, and vibration from the moment we leave port.
We favor coastal routes for flexibility, ports of refuge, shorter legs, and better options if weather shifts.
Weather windows are rules, not suggestions. If waves or wind cross limits, schedules change.
For blades, wind is the enemy. Even at sea, we protect edges and watch every strap.
At night, the work continues. Periodic checks, tension inspections, and sensor reviews.
Arrival isn't the finish, because unloading can be harder than loading.
We've reached Dongying, but docking is only the start of the most careful part, unloading.
At the receiving port, alignment is everything. Ramp grade, deck height, and ground capacity must match.
Before we move weight, we secure the ground because the quay becomes part of the machine.
This is centimeters work. Slow, controlled, and constantly verified.
Every hold point gets locked, marked, and recorded because gravity never pauses. Blades are long and wind sensitive. Unloading is a balance between control and clearance.
Once ashore, we solve the puzzle. Everything is staged in the exact order and the site will need it. We inspect again, surface, seals, and sensor logs, because transport can create damage you won't notice until it's too late.
This isn't a random yard. Dongying is a testing and certification base where the turbine will be assembled and proven. The last mile to the erection site is short in distance, but brutal in constraints. Here the ground is the first challenge. Before cranes arrive, the site must be stabilized with piles and engineered pads. We measure the site like a machine because cranes demand flat, stable, predictable ground.
To lift components at this scale, we bring a crawler crane in the 4,000-ton class. A crane this big is built like a structure. Every pin is inspected, every lock is verified. Even parking the nacelle is engineering. Load distribution and ground pressure are managed step by step.
Blades wait like aircraft wings, protected, restrained, and positioned for the safest possible lift.
Before any lift, we rehearse on paper, because at 200 meters, there's no room to improvise.
Transport brought the pieces here. Now the crane will turn logistics into a standing turbine.
Today we are not building parts, we're building height, nearly 200 meters, in wind that never waits.
Wind is the real deadline here. Miss the window and the whole lift stops.
This is the heaviest piece. Move it wrong once, and you lose days.
At this scale, every centimeter is planned. Center of gravity, lift points, and the wind limit.
If the wind stays inside the limit, we lift. If it doesn't, we wait. That's the rule.
Because once this machine is in the air, there's no pause button.
Before we lift anything, we build the site. Zones, lanes, and a work flop that keeps people and machines separated.
This ground is coastal and soft, so we stabilize it first with piles and engineered layers to carry extreme loads.
A crane pad is a measurement problem. Flat, stable, predictable, or we don't lift.
We control people flow as tightly as load movement. One step into the wrong zone can stop the day.
These mats are our temporary road, load distribution, traction, and a safe path for SPMTs and modules.
The lift plan is the contract. Rigging geometry, wind limits, hand signals, and abort rules are locked before metal moves.
Clear communication is a safety system. One crane, one signaler, one set of commands.
When the site is ready and the wind is inside limits, we switch from planning to lifting. Power erection is precision stacking. Each section must land within millimeters, or the whole line leans.
Rigging comes first. Correct lift points, correct angles, and every pin double-checked. We lift slow to keep it stable. Rotation is managed, not tolerated.
This is the critical moment. Steel meets steel, and the bolt pattern must line up perfectly.
After the set, we measure verticality. Numbers decide whether we proceed.
Bolts are tightened in sequence, torque values, star patterns, and verification marks to prove it. Each new section multiplies consequences. Alignment errors grow with height. We verify flatness and contact, because gaps become movement, and movement becomes fatigue.
When the tower is straight and the joints are proven, we earn the right to lift the nacelle.
This lift is a turning point. The nacelle is the turbine's core, and one clean set can decide vibration for decades.
We don't lift by intuition. Center of gravity and lift points are confirmed before the hook moves. At this scale, rigging is geometry, angles, loads, and redundancy.
Wind decides the schedule. If it rises, we stop. If it falls, we move.
We lift slow, stabilize, then climb, because swinging is the enemy. Now the target is a ring of steel, small in tolerance, huge in consequence. This is centimeters work. Match the bolt circle, protect the surfaces, and keep the load steady.
A clean touchdown means no forced fit, and forced fits become vibration later.
We lock it mechanically. Torque patterns, verification marks, and final checks before we release the crane.
When the nacelle is seated and verified, the turbine finally has a heart. Now we give it wings. Next comes the hub, the mechanical handshake between the nacelle and the blades. Even smaller parts at this scale can be unforgiving. Lift geometry must be exact. Rigging is built for control. No twist, no side load, no surprises.
We stabilize before we climb, because rotation near the tower is a hazard.
Now we're aligning heavy steel in midair, and this is where patience prevents damage.
A clean seat means no preload, no hidden stress waiting to become vibration. We lock it with torque discipline, sequence, value, and verification marks. Then we connect pitch, the system that turns blades to control power and survive gusts. If pitch responds cleanly here, we're ready for the most wind-sensitive step, installing the blades.
Now we install the blades, 153 meters each, and wind becomes the boss.
If crosswind crosses the limit, the lift stops, because a blade is a sail.
We lift with a yoke to control angle and protect the composite. No crushing loads, no twist.
Even in calm air, a blade flexes. Our job is to keep it stable, aligned, and predictable.
Up here, the target is a bolt circle. Small tolerance, massive leverage. We use pitch to reduce wind force. Feather position keeps the blade from fighting us.
This is centimeters work. Align first, then touch. Never force.
A clean seat prevents hidden stress. Hidden stress becomes vibration.
lock the route with controlled torque, sequence, value, and verification marks.
One blade at a time, because control beats speed when the wind can change in seconds.
When the third blade locks in, the turbine finally looks like what it is, a power plant built to spin.
Now the lifting stops, and the testing begins. Now we bring the turbine to life by connecting its power, grounding, and control systems. Every HV connection is treated like a critical joint. Seat, lock, verify.
Grounding is non-negotiable. Before we export power, we prove the machine is safe.
We test insulation margins now. Salt air and humidity punish weak protection. Then we connect the nervous system, SCADA, sensors, and the networks that carry every decision.
Commissioning is mapping. Every sensor must report the truth before control can act.
We test the safety chain, interlocks, emergency stop, and protective modes, because fail-safe matters more than output.
We arm storm behavior, because offshore wind can go from calm to violent in minutes. When power, control, and protection agree, the turbine is no longer a structure. It's a system ready to move.
This is the first real moment when a machine this big moves under its own control.
We start at the lowest speed, because first motion is about observing, not producing.
At low speed, we look for smoothness. No oscillation, no unexpected noise, no drift.
Vibration is the truth signal. If something is wrong, it shows up here first.
Next, we calibrate yaw, steering the turbine to face the wind without overshoot.
Pitch is our throttle. Small angle changes control loads and power.
We ramp speed in steps, hold, measure, and only then move to the next band.
Certain speeds can excite resonance, so we pass through carefully and confirm the structure stays quiet. Heat tells the same story. If friction or load is wrong, temperature climbs.
After the first run, we stop and inspect because early checks prevent late failures. Now comes the milestone. First, power export, under strict control.
Grid connection is where testing becomes real. Everything must protect itself and the network.
When the breaker closes, the turbine is no longer isolated. It's part of a larger system.
We ramp power in steps, hold, measure, then step again.
Outside, it looks simple, but inside, every variable is being watched. Power electronics are the limiter. Temperature and voltage decide how fast we can climb.
As power rises, loads rise, so we watch vibration, torque, and temperature as one story.
Every step becomes evidence, because this phase is about proof, not just performance.
First export is not the end. It's the start of long-term validation.